Hello all, we shall look into the next module, which is angle modulation. Okay, in this angle modulation, as was discussed earlier in the previous module, when we were talking about the basics, in angle modulation two different types are there. One is a frequency modulation, other one is phase modulation. Both of them look actually alike because they all belong to the angle part of a carrier. So it's the angle which is getting changed every time when you perform this kind of modulation, but there is a slight difference. So they're almost identical with a slight difference in between them. Okay, so we shall try to understand it. So what is basically the definition of these are all the things that we'll be talking about in angle modulation. Basic definition: frequency modulation. We'll be talking about narrow band and wide band, FM transmission. Then we'll talk about the bandwidth of FM signals, generation of FM, demodulation. We'll also talk about the stereo multiplexing. Then we'll talk about PLL, nonlinear effects in FM, super heterodyne receivers, and all those things. Okay. So coming to the definition of angle modulation, we have already seen the AM definition. S of t is equal to AC into 1 plus M of t cos of omega ct. This type of modulation basically changes the amplitude of the carrier. If you can observe, 1 plus M of t is present before cos omega ct, okay, which is the amplitude part. Now when you try to put the the variation in the angle of carrier, so obviously it comes within the cos, and you can see that in the next slide, the second slide, S of t, next equation right here. S of t is equal to AC cos of omega ct plus theta of t. So amplitude would remain constant, but the angle is getting modulated or changed. Such a kind of technique is what is called angle modulation. So this omega ct plus theta of t, which is in total the angle part, it can make even either the phase or the frequency to change. So this is about the angle modulation part. So how do you represent basically the angle modulated signal? So we have already discussed about this. Special cases for the phase modulation, the phase is directly proportional to the modulating signal, that is theta of t. And for frequency modulation, the phase is proportional to the integral of M of t, so that theta of t becomes equal to df integral minus infinity up till t M of sigma d sigma, okay, where frequency deviation constant df has units of radians per volt second. So this deviation is very, very important. So what is the equation for instantaneous frequency? We can write it as omega I of t is equal to d psi of t divided by dt, where psi of t can be written as integral minus infinity till t omega I, which is nothing but the instantaneous angular frequency, and a function of some variable sigma, t sigma, where psi of t is omega ct plus theta of t. So phase modulation occurs when instantaneous phase is varied in proportion to that of the message signal. Okay, that's the difference. So how do you write a frequency modulation? Frequency modulation occurs when the instantaneous frequency is varied linearly with the message signal, as we know it already. Okay, so what will happen to omega I of t? Omega I of t is omega c plus df of M of t, where theta of t becomes equal to df integral minus infinity till t M of sigma d sigma. So the resulting FM will be S of t is equal to AC cos of omega ct plus df integral minus infinity till t M of sigma d sigma. So this becomes the equation. So how do you basically see the block diagram for a frequency and a phase modulator? So you have M of t, you integrate it, that is when you get integral, and then you will have MP of t, and then you basically use a phase modulator. So this integral M of t would come and sit at the phase part, which is theta of t. So if you can go back and observe, this equation, write this equation right here. If you observe this equation, theta of t is basically the phase part of it. Okay, so now this equation says that this equation would suggest that in the theta of t part, which is a phase part, you basically see integral m of t coming and sitting. So that is why this kind of block is put here. So after integration, you put a phase modulator, it becomes a frequency modulation. So the vice versa is the phase modulator block. What is it? You see a differentiation being done, and then you put a frequency modulator. So once you have m of t with a differentiator, and then you put a frequency modulator, in theta of t part, you would already have an integration sign, and now you are differentiating m of t. So what you get is basically m of t itself. So you will have m of t sitting at theta of t part. So that becomes the phase modulation. So even though phase modulation is not there in the syllabus, we had a small discussion on that. So when you have a sinusoidal modulating signal, if a band pass signal is represented as s of t equal to r of t cos psi of t, where psi of t is omega ct plus theta of t, then the instantaneous frequency of FM signal is given as fi of t, which is equal to fc plus 1 over 2 pi d theta of t divided by dt. Similarly, the frequency deviation, that is the amount of deviation which happens when the modulating signal is applied, you will have it as d of t, which is equal to f of t minus fc, which is equal to 1 over 2 pi integral, d by dt of theta of t. So the peak deviation will be delta f, which is maximum of 1 over 2 pi d theta of t divided by dt. And delta f is related to the peak modulating voltage, which can be written as delta f equals 1 over 2 pi df vp, where vp is a maximum value of m of t, which is the peak voltage. So peak to peak deviation will then become delta f, which is max of 1 over 2 pi d theta of t by dt minus minimum of 1 over 2 pi d theta of t divided by dt. Okay. What are the advantages and disadvantages of angle modulation? Constant advantages, constant amplitude means efficient nonlinear power amplifiers can be used, which is very advantageous. Superior signal to noise ratio can be achieved in comparison to that of a FM if bandwidth is sufficiently high. Okay, these discussions, at least the second one, we'll have it in the module number 3 when we talk about the noise in the amplitude or noise and analog modulation techniques. Okay, there we'll try to derive the expression for signal to noise ratio at different points and see how it is superior to AM. Disadvantages usually requires more bandwidth than AM. It's more complicated hardware. Okay, this is a disadvantage of it. So we'll also try to now summarize the things that we discussed. The peak phase deviation is given by delta theta, which is maximum of theta. Delta theta is basically related to the peak modulating voltage by delta theta is equal to dp into vp, where vp is the maximum modulating signal voltage. Phase modulation index beta p is delta theta. Frequency modulation index is given by delta f divided by b, where delta f becomes the frequency deviation, b is the bandwidth. So normally we can write it as 2fm. Spectrum of PM or FM signal with sinusoidal modulating signal. So this equation I think we can understand. This is a basic Fourier series where we have brought in the Fourier coefficient Cn into consideration. So when you try to expand this, what we get is finally the equation for g of f, which is equal to AC into summation n equals minus to plus infinity Jn of beta delta f minus nf. This equation is quite important for us, where Jn is basically the Bessel's function. Okay, Jn equation is put right here. Okay, so you can observe 1 over 2 pi integral minus pi to plus pi e to the power j beta sine theta minus n theta is what is basically Jn of beta. So we take the help of Bessel's function in defining the equation for a Fourier frequency modulation, so that we get to know what is actually the total bandwidth of a FM signal. So this is how the Bessel's function will look like when you plot it for the first order. Okay, and these are all for different n values, n equals 0, 1, 2, 3 for a specific beta value, which is 2, 4, 5, 5.2 and so on. Okay, so frequency spectrum, now as we have already gotten to know what is the equation in the previous slide, we can write it as s of t equals AC summation n equals minus to plus infinity Jn of beta cos omega c plus n omega whole multiplied by t. Okay, from this equation it can be seen the frequency spectrum of an FM wave with a sinusoidal modulating signal is a discrete frequency spectrum made up of components based at frequencies at omega c plus or minus n times of omega m. Now we can see the discrete spectrum component spaced at omega c plus or minus n omega m. Okay, so by analogy with the AM, these frequency components are basically the sidebands, isn't it? Because there we had only two sidebands, now we have got infinite number of sidebands, so which would only mean that you know the bandwidth in case of a frequency modulation can go up till infinity, theoretically speaking. So this is how the spectrum will look like. So we have restricted ourselves to only beta equal to 5, wherein I've got this much of frequency component. So as and when the beta increases, you can also expect the frequency components to raise. So as per the Carson's rule, this rule is basically used to define the bandwidth of a FM signal. Although the sidebands of the frequency FM signal extend to infinity, it has been found experimentally that signal distortion is negligible for a band limited FM signal if 98% of the signal power is transmitted. Based on the Bessel's function, 98% of the power will be transmitted when the number of sidebands transmitted is 1 plus beta. So take some beta value and you see 98% of the power will get transmitted when the number of sidebands goes up till 1 plus beta. So this is what is basically the Carson's rule. Okay. So based on that, you can say 1 plus beta is up till Fc plus 6 times of Fm. So finally, we can write what is Carson's rule, which will take care of the bandwidth of Fm, which is 2 times of beta plus 1 whole multiplied by B. For a sinusoidal modulation, B is nothing but equal to Fm. Okay. So bandwidth of an FM signal is given by beta Vt equals 2 beta plus 1 times of Fm. Okay. When beta equal to 0, baseband signal will have Bt equal to 2 Fm. So now we'll talk about a narrow band angle modulation, okay, where we have an integrator, we have got oscillator which generates a frequency of omega c, and we have a 90-degree phase shifter, a negative 90-degree phase shifter, which gives me AC cos omega ct minus AC theta of t sine of omega ct. Okay. So generation of a wideband is done like this. You have a limiter, you have a frequency multiplier, you again have a limiter and then a frequency multiplier. This kind of method is also called as the Armstrong method. Or it can also be defined as an indirect method of FM generation. You start with a narrow band signal. Okay, narrow band block is put right here. So using this, you generate a narrow band and then you arrive at the wideband by applying many frequency multipliers with limiters, or I can say kind of mixers. So direct method is using frequency discrimination as well as the zero crossing detector. So one is frequency discrimination, other one is the zero crossing detector, indirect method. Okay. So coming to the indirect method, as I told, it's also called as Armstrong method, where you first use a narrow band FM and then use frequency multipliers to increase the frequency deviation to the desired level. These type of demodulators use a PLL to match local oscillator to modulate the carrier frequency, because normally we have a incoherent receiver, because the frequency of the transmitter carrier and the receiver carrier will not be most of the time matching, because it will always have a phase. So PLL will basically track the variation. So requirements of FM detector. FM demodulator must satisfy the following conditions. Number one, must convert the frequency variation into amplitude variation. That's the basic thing. Conversion must be linear and very efficient. This is very, very important, because if it becomes non-linear, the demodulated signal may not be matching with the modulating signal which is at the transmitter. Demodulation circuit should be insensitive to amplitude changes. It should respond only to the frequency changes. Okay. It should not be too critical in its adjustment and operation. So coming to the first kind of demodulation, which is frequency discrimination or a simple slope detector, we use a slope circuit and an envelope detector. So basically AM demodulator is used here. Before that, a slope detector is used. Let's see what is the slope detector here. This is what is basically a slope detector. Okay. So a slope detector consists of two units, a slope circuit and an envelope detector. The slope circuit converts the frequency variation in the FM signal into a voltage signal which resembles an AM signal. The envelope circuit obtains output signal proportional to the message signal. Okay. So I think we should stop at this point for now. In our next class, we shall try to understand the circuit in a much more better way.